going to solve a problem not unlike the Coulomb blockade, but in a limit where the state that mediates the tunneling between the left and right electrodes does not change its energy on charging. So how do we do this? Well, this is in fact a fairly simple problem to solve. So drawn out here is some representation of a barrier of height V0, and let's make the thickness on the left x left, and then a bound state in here, and I'll just draw in an allowed energy level E0, and then the second barrier of length x right. This is solved just as we solved one-dimensional tunneling problems in Chapter 2. So supposing an electron of energy E is incident on this barrier, we start off with a plane wave from the left. We match the wave function and its derivatives at this point, this point, this point, and this point. The setting up of this middle barrier region, let's just call it D in thickness, is a little tricky because this is not an infinite well, and it turns out that a transcendental equation has to be solved for this problem. But nonetheless, it's fairly straightforward one-dimensional quantum mechanics. The transmission through the left barrier we'll write down in the limit of small reflections of the barrier being equal to e to the minus 2m v0 minus e over h bar squared square rooted times x left, then with a similar expression for x right. The result of doing this is a remarkably simple appearing formula called the Bright-Vigna formula. It's been multiplied by the quantum of conductance for one channel, so we haven't multiplied by 2 to allow for 2 spins per quantum channel, and here it is. These are the two transmission probabilities through the left and the right barrier. There is a resonance denominator here, and then this term here. Now this formula has a remarkable property. If the incident electron has an energy equal to the allowed state in the gap, and in the limit where we make XL equal to XR, so that gamma left equals gamma right, this formula produces a striking result. At resonance, this term disappears. This term just becomes 4 gamma squared, and we have gamma squared on top, and so we arrive at the solution that G is E squared over H, or if we take account of the fact that 2 spins can occupy this channel, we get G is 2 E squared over H. This thing appears to look like a quantum short circuit when the resonance condition is met, i.e. when the electronic energy is equal to the energy of the bound state in the gap, and when the barriers are symmetrical, apparently completely independent of the height of the barriers. The simulations in the picture below show the transmission probability for a tight binding model of a molecule in a gap, and every time there's a logarithmic scale of transmission here on the left, and every time one hits a resonance, the transmission goes shooting up by orders of magnitude, the width of these peaks here reflecting the values of gamma left and gamma right. So apparently this formula is saying that one could tunnel from the Earth to the Moon via a resonant state on a satellite halfway between the Earth and the Moon. Actually, this is completely untrue, because remember, we started this with the assumption that the state in the barrier did not change energy during the tunneling process, and clearly that is not the case for the Coulomb blockade. Here are some simulations by a colleague of mine, Kevin Schmidt, of the time evolution of probability as a wave packet is incident on a barrier. So in panels A through D, the wave packet appears from the left, is propagating towards the barrier. The barrier is shown by these, there's the resonant state in the barrier, and we have high energies on atoms each side of it to act as potential wells. What we see is that the wave packet hits the barrier, and if we solve for the time development of the probability amplitude and square it to see what's happening to the electron, we see that as time progresses, probability starts to build up on this central state. In other words, it begins to charge. What happens is this probability continues to increase until the transmission out of the right barrier is just equal to the incident flux on the left barrier, and at this point the system goes into equilibrium, but it has charged. The panels on the right show the situation for a larger barrier. You can see that the two barriers are spaced by a bigger amount, and you can see that the charging is much larger. So, if the barriers require a build-up of charge on the central atom in order to propagate the electron out of the right barrier, we're back to the Coulomb blockading problem, and resonant tunneling will not occur because the energy of the state that the electron sits on will shift with charging. You see in this picture a picture somewhat between the simple Coulomb blockade picture, where an entire electronic charge sits on the state in the barrier, and the resonant tunneling problem, where we have assumed no charging. What is the condition for resonant tunneling? Well, it turns out that resonant tunneling occurs when gamma left and gamma right are on the order of unity. In other words, when a metallic contact is formed. What is this? Well, let's just imagine a row of metal atoms, all with a state associated with their valence electron at the same energy. And now, let's simply insert one more metal atom into this gap here. Resonant tunneling, then, is simply the delocalization of electrons on this lattice that we talked about when we discussed tight binding. In the event that the barriers each side of this atom are made weaker, charge begins to build up, and we go away from the picture of resonant tunneling. As we will see in Chapter 8, resonant tunneling probably never occurs in molecular systems. One requires solid-state systems so that their energy does not change significantly on acquiring charge.